Alright, so let's do the part 3 of lecture 2. So we are going to actually move into this electrons now. So just like light, the electron itself is actually wave and particle at the same time. So it is more like particle for the electrons, but yeah, it's still the same particle wave duality actually holds for the electrons too. So I want you to actually watch the videos. This is the original videos done by the I think it's a Hitachi companies who actually made these videos, but they actually demonstrate the dual slit experiment just like the light experiment, but this time around they actually sent off this one electron at a time, and then they see this diffraction patterns just like the wave particle do, a wave actually do. So it's demonstrating the wave nature of the electrons there. And once you watch this one right here, then I actually want you to watch the this one too. That one is associated with Heisenberg uncertainty principle, but this one is actually done by the photons, using photons. But you can actually do the similar stuff with the electrons too, but I think it's a little bit more costly to do the experiment, so most of the people actually do it with the photons, although that photon actually have a little bit more complicated uncertainty principle. So technically speaking, I would rather actually try to show you the experiment done by the electrons, but it's not available on the YouTube. So at this moment, we just have to deal with photon uncertainty principle experiment. So by studying the electrons, the nature of the electrons, there are two important formulas that you have to remember for the exam. One is the de Broglie relations, which is I think I'm probably saying it in a wrong way. De Broglie is probably how it's actually supposed to sound, but I'm not really sure. But anyway, it says that wavelength is equal to Planck constant divided by momentum. P is the momentum, okay? So that one is actually called de Broglie relations. So P, that's momentum, is actually equal to mass times velocities, which is the speed. So Planck constant divided by mass times velocities, or speed. So that's the de Broglie relations. So it says that momentum and wavelength is inversely proportional. And because of this particular findings, they can actually find this wave-particle dualities not only for the light, but also some other particle as well, much heavier stuff, like electrons. So once we actually accept this formula, then we can actually move on to this Heisenberg uncertainty principle. That is a little bit more strange. You can actually learn these things from the I think that was Fourier transform that you if you decide to go with the chemistry major in the second year in my class, we are going to use a mathematical tool called Fourier transform to actually figure out this Heisenberg uncertainty principle. But right now for the general chemistry one, all you have to know is that it is impossible to find the exact position and the exact momentum at the same time. In formula, uncertainties, the wiggle room in the position x multiplied by the wiggle room in the momentum, which is uncertainties related to the momentum, has to be bigger than Planck constant divided by 4 pi. So the right hand side of this equation is constant, and multiplication of uncertainty in position with the uncertainty in momentum has to be larger than this constant. So in a way that if you know that the information about the positions very good, then that you're gonna lose the information on the momentum. So that's pretty much what it says. And because of this particular uncertainties, the electrons actually you can't really pinpoint the position of the electrons, and that's really a problem because when you try to figure out the position of the electron inside of the atom so that you can actually calculate the energy of the system, you can't do that. So the guy named Schrodinger actually trying to find the alternative way of actually calculate the energies. So he come up with this awful looking formulas. It's called the Schrodinger Equations, and it turns out that this formula is really good, and you can actually find the solution, which is solution is actually the, not the numbers for this one, it's actually the functions, or it's called the wave functions. And as long as you know the wave functions, you can actually find out you can actually calculate the all property of the molecules, or what's going to happen to the reaction, and so on and so forth. So this formula is particularly important for chemists like me, who actually use this formula to actually calculate the property of the molecule, and so on and so forth. So that's the Schrodinger equation. That's the central topic of the quantum mechanics for the chemist. And if you can actually solve these equations, then you can actually predict what's going to happen to the reactions. So as I said, that in the classic way, like Newton used to do, is that if you can actually pinpoint the position of the nucleus and then pinpoint the position of the electrons, then all you have to do is to use the Coulomb formula to actually find out what is the interaction here, what is the interaction between the electron and electrons, and then how fast the electrons are moving around with respect to the position of the nucleus. You can actually find the energy of the molecule, but that's not allowed for the tiny particle like electrons. Instead, you are going to use the Schrodinger equations, and that Schrodinger equations, the solution to the Schrodinger equation, this part is really important, so I want you to memorize these portions. The solution to the Schrodinger equation is actually called orbital, and then that orbital, technically speaking, it is different, but that's okay. The orbital, the solution to the Schrodinger equations is the orbital, and then that orbital, if you actually square the orbital and take the absolute value of it, then you can actually figure out the probability of finding the electron at that spot. So square of the orbital is going to give you the probability of finding electron at that position. That's the information hidden inside of the orbital. Square of that orbital is going to give you the probability of finding the electron at any positions. And that because you can actually solve for the orbital using this Schrodinger equations, you can actually figure out the shape and the position and the size of these orbitals, and then you can actually use computer to solve the electron-electron interactions or the electron-nucleus interactions. In other words, that you can actually calculate the whole energy of the molecule. That means that you can actually predict what's going to happen to the reactions. So basically, all of the stuff written here is exactly what I said. It's the Schrodinger equations. The solution is called orbital, and then that orbital is going to give you the position, size, and shape of the electron cloud if you square it. And our goal for the next lecture is going to be assuming that you have enough mathematical background, and then you can actually write out the computer program to actually compute for the shape of the orbital and so on and so forth. We can actually do quite a bit of the prediction of what's going to happen to the chemistry, and we are going to start working on that portion in the next videos.